This lecture is about the SN2 reaction. Here's the basic idea. Look at the following reaction of methyl iodide and hydroxide. Iodide is being displaced by hydroxide, so we call iodide the leaving group. It's departing from the carbon. Hydroxide is the nucleophile because it's attracted to the partially positive carbon, which is nuclei-like. So nucleophile loves nuclei. The partially positive sp3 hybridized carbon is the electrophile because it's attracted to the electrons of hydroxide. Now if you double the concentration of methyl iodide, you'll double the rate of the reaction. If you double the concentration of hydroxide, you'll also double the rate of the reaction. And doubling the concentration of both methyl iodide and hydroxide will quadruple the rate of the reaction. Thus, the rate of the reaction is equal to K, the rate constant, times the concentration of methyl iodide, times the concentration of hydroxide. Since both methyl iodide and hydroxide are first order, you add those orders and the overall rate order is 2. We call this type of reaction substitution that is nucleophilic and second order, or SN2. So what is the nature of this leaving group? Well, leaving groups are the conjugate bases of strong acids. And the reason that they like to leave or pop off of the partially positive carbon is the same reason they like to give up a proton. They don't like to attach to things that are positive. They're easily displaced. For example, the halides, iodide, bromide, and chloride, are all the conjugate bases of the strong acids, hydroiodic acid or hydrogen iodide, hydrobromic acid or hydrogen bromide, and hydrochloric acid or hydrogen chloride. These are well-known strong acids from general chemistry. The sulfonates, represented by negative charge on O3Sr, where R is a carbon group, they are the conjugate bases of HO3Sr, which is a sulfonic acid, a strong acid like sulfuric acid. The relative rates of displacement of the leaving groups are the following. The sulfonates are the most easily displaced. And then that's followed by iodide, which is knocked off faster than bromide, which is displaced much more quickly than chloride. And then this order is based on the strength of the acid from which each of these conjugate bases is derived. So the sulfonates come from the strongest acid, and the chloride comes from the weakest of the strong acids. So what is the nature of this electrophile, that sp3 hybridized carbon with a partial positive charge attached to the leaving group? Let's take a look at the relative SN2 reaction rates. The methyl halide or sulfonate reacts the fastest. It's the least sterically hindered, so when a nucleophile comes in to displace the leaving group, the reaction occurs in seconds if you're working in molar concentration. That's faster than the primary halide or sulfonate, which will react in minutes. The primary halide has an R group, that's an extra carbon, attached to the CH2. The primary halide reacts much faster than the secondary halide or sulfonate, which would take hours at room temperature at molar concentrations. So now there are 2 carbons attached to that carbon, the electrophilic carbon with the leaving group, creating a lot of steric bulk. At this point, if you put a 3rd carbon on that electrophilic C, you're going to have such a slow reaction that for all practical purposes, this is not going to work. So a tertiary halide or sulfonate will not undergo an SN2 reaction. Another reaction may occur, but it won't be SN2. Okay, now when a nucleophile displaces the leaving group in an SN2 reaction, it doesn't come from the same direction as the leaving group. So the nucleophile comes around the back, okay? It comes from the side opposite of the bond between the carbon and the leaving group. Doing that causes what's known as inversion of configuration. So if you look at example A, The N3 minus or azide anion is the nucleophile. It comes from the rear of the bond between carbon and bromine, bromine is the leaving group, and displaces it. So you see there's an arrow coming from the azide anion, which then comes at the carbon, so the arrow heads at the carbon. That breaks the bond, so we start with the electron arrow from the middle of the carbon-bromine bond, and those electrons are going to end up on bromide, so we showed that arrowhead pointing toward the Br atom. So the result is that the N3 group is now pointing up, and the Br minus is displaced. So think about this. Bromide was originally pointing down. Azide is pointing up. So you notice they're pointing in opposite directions. That's the inversion of configuration. In example B, we have a stereogenic center. The chloride is pointing toward us. So the azide anion, the nucleophile, has to come from the back. And when it comes in, it displaces the chloride. Azide ends up in the rear. It ends up in the back. See the dashed line? That pushes the hydrogen, which was in the back, toward the front. That's inversion of configuration. Now, inversion of configuration only matters if the reaction gives you a different diastereomer. Like in example A, we start with a trans diastereomer and we end up with a cis diastereomer after the SN2 reaction. Or, as in example B, you have a single enantiomer reactant. When it reacts with azide and you get inversion of configuration, you get an enantiomer of opposite configuration. That is, imagine if you replace the azide, the N3, in the product with Cl. Wouldn't that be the opposite enantiomer? So we say that the replacement of the chloride by the azide achieves inversion of configuration. We've created the opposite configuration of the enantiomer. Now, the nature of the electrophile in terms of hybridization is that the carbon with the leaving group must be sp3 hybridized. That is, it has to have 4 single bonds. Except under certain special circumstances, if the leaving group's attached to a carbon-carbon double bond or a carbon-carbon triple bond, the nucleophile can't displace it. It can't knock it off. So you won't get SN2 with these types of electrophilic carbons. So if you look at the examples below, the carbon-bromine bond has an sp2 hybridized carbon, so azide is not able to perform an SN2 reaction. And in the example below that, the carbon-bromine bond has an sp hybridized carbon, so again, there is no reaction with azide. The reason for this is that the higher S character in the sp2 and sp hybridized carbons causes the carbon-bromine bond to be shorter and stronger. If you think about sp3, only 1/4 of an sp3 hybridized orbital is S character, for 25%. Whereas with sp2, it's 1 out of 3, so that's 33%. And the more S character, the shorter and stronger the bond will be. So that would explain why sp2 hybridized orbitals in a bond to a leaving group would be stronger than sp3. Similarly, with an sp hybridized orbital, that means that if you have 1 out of 2 of those orbitals is S character, which means you have 50% S character, and that would be the strongest kind of sigma bond to the leaving group. Again, making it impossible for the nucleophile to displace the leaving group. Since the nucleophile has to come behind the bond between the carbon and the leaving group, that explains why steric bulk will slow down the reaction. So this inversion of configuration, which demands that the nucleophile come from the rear of the carbon to leaving group bond, correlates with the slowdown of reactivity when there's a lot of bulk, a lot of atoms attached to the electrophilic carbon. That explains why a tertiary carbon with a leaving group won't perform SN2. But also a neopentyl group, shown in red, will also not perform SN2 reactions. The methyl groups in neopentyl bat the azide away, keeping it from reacting with the electrophilic carbon. Practice problem 1. Predict the major product or products of each of the following SN2 reactions. If no reaction occurs, explain. So here are some of the things you want to look for. First, you want to make sure that you have a carbon that is sp3 hybridized, remember 4 sigma bonds, connected to a leaving group. And remember the leaving groups are chlorine, bromine, iodine, and a sulfonate. Also, you have to have a nucleophile, which in this case is always going to be a negatively charged species, an anion. And don't forget that with SN2 reactions, you can get inversion of configuration, and that will be obvious if you have either a change in the diastereomer or a change in chirality, changing from one enantiomer to a new enantiomer. You also have to worry about the no reaction cases. Let's go over those. A tertiary carbon with a leaving group does not react by SN2. It's too bulky around the reactive carbon. Neither does a neopentyl carbon attached to a leaving group. The tertiary methyl groups attached to the primary carbon smack away the nucleophile, preventing it from getting at the carbon. Then of course we have the sp2 and sp hybridized carbons with the leaving group, for which the bond to the leaving group is too strong because of the enhanced S character. At this point, you want to pause the video so that you can work on the practice problem. Then you can continue the video to see the answers. Answers to practice problem 1. In problem A, hydroxide causes inversion configuration, displaces chloride, and you form the alcohol plus chloride. In problem B, azide is not able to displace fluoride because fluoride is not a leaving group, so there's no reaction. In problem C, you have a choice between fluoride or chloride as a leaving group, and only chloride is acceptable. So azide displaces the chloride, forming the new product plus chloride. In problem D, thiolate anion, HS-, comes from the front of the carbon because the leaving group, the sulfonate, is in the back. See the dashed line? That causes inversion of configuration, which would give you a product in which the thiolate, now a thiol, is pointing towards you in the front, displacing the sulfonate as a leaving group. In problem E, now the sulfonate's towards you. So the thiolate anion, SH- comes from the back and produces the opposite enantiomer. In problem F, you have a bromide pointing up. So the nucleophile, CN- or cyanide, comes from the bottom, displacing bromide, giving you a new diastereomer in which the cyanide is pointing down. And in problem G, the cyanide is going to attack from the top because the bromide is pointing to the bottom. In the final product, the cyanide is pointing up. Practice problem 2. Predict the major product or products of each of the following SN2 reactions. If no reaction occurs, explain. The same principles apply in problem 2 as they did in problem 1. The nucleophile will be negatively charged. And notice the nucleophile is typically written over the reaction arrow. You'll see this in a lot of organic chemistry textbooks. In E, azide is going to react somewhere, so I'm kind of giving that away. But in that product, I want you to draw out the complete structure of azide once it's attached to the carbon. I don't want you to hide anything. I want to see all the bonds, all the charges, so that I know that you know what an azeto group looks like when it's attached to a carbon. At this point, you want to pause the video so that you can work on the practice problem. Then you can continue the video to see the answers. Answers to practice problem 2. In problem A, methyl bromide reacts with a nucleophile containing a negatively charged oxygen. The negatively charged oxygen displaces bromide to form an ether. In problem B, hydroxide does an inversion of configuration, displacing chloride and reacting from the left side of the molecule since chloride is on the right side. In problem C, there's no reaction because iodide is attached to a neopentyl group, which is too bulky for SN2. In problem D, thiolate anion, HS-, reacts exclusively at the primary iodide at the top of the molecule because the other iodide is part of a neopentyl structure. You look at the area right next to that primary alkyl iodide, there is a tertiary carbon attached to it, which makes it neopentyl, so there's no reactivity at the bottom portion of the molecule, only the top portion. In problem E, there is an inversion of configuration as the azide anion displaces the bromide. Now in that case, you're showing the entire structure of azide, and you can see there are two double bonds between each pair of nitrogens, a plus charge in the middle portion of the molecule and a negative charge on the end. So the net charge of the azide group is neutral. The other carbon-bromine bond does not react in that molecule because it is sp hybridized, making the bond too strong for SN2 reaction. In F, there is no place for the azide anion to react. You either have a tertiary alkyl bromide or an sp2 hybridized carbon-bromine bond, which is not able to react either. In problem G, you have one spot for SN2 reactivity, which is the primary alkyl bromide, and azide displaces that to form the final products. Okay, we've looked at the nature of the leaving group and the electrophiles. Now let's look at the nature of the nucleophile. In general, if you have a negatively charged nucleophile, it'll react much faster than if you put a proton on that, because the negative charge is able to sense or react more rapidly at the partially positive carbon than when it's neutral and only slightly negative. So for example, the acetate anion, CH3CO2-, reacts faster than acetic acid, CH3CO2H. So much so that you'd never want to use acetic acid as a nucleophile. It would be a waste of time. You also need a lone pair to be an SN2 nucleophile. This may seem obvious, but a lot of people forget about that. For example, ammonia, NH3, is a nucleophile. As soon as you put a proton on the only lone pair that's available, now it's NH4+, the ammonium ion. That's not a nucleophile. Okay, it can't react with a carbon with a leaving group. Okay, only a few neutral nucleophiles, like ammonia we just saw, are reactive enough for practical SN2 reactions. We have the ammonia and the amines. On the amines, you have to put at least one carbon on the nitrogen, so you have R3N, which is a tertiary amine, or R2NH, 2 carbons, that's a secondary amine, or RNH2, which is a primary amine. Then you also have the phosphines, where you have carbons attached to phosphorus, anywhere from none, which would be pH3 phosphine, all the way up to 3. These are two examples of neutral nucleophiles which are very good for SN2. Water, alcohols, and ethers are worthless for SN2. Don't even think about trying to use those unless you want to put the reaction in a container and put it under high pressure and high temperature. The reactions will go exceedingly slowly. So we don't ever think about water, alcohols, or ethers as SN2 nucleophiles. In solvents that hydrogen bond, called protic polar, which are solvents that contain OH or NH, the reactivity of the nucleophilic atom, which is the one that can donate a lone pair to the partially positive carbon, increases as you proceed down a group in the periodic table. So for example, in water, which is a protic polar solvent, HSe- is more nucleophilic than HS-, which is more nucleophilic than hydroxide. And that's because selenium is lower in group 6 than sulfur, and sulfur is just below oxygen. The size of the nucleophile in this case is what makes a difference. The bigger nucleophilic atom is more reactive than the smaller nucleophilic atom. In solvents that do not hydrogen bond, called aprotic polar, that is, they have no OH or NH, the reactivity of the nucleophilic atom will decrease as you proceed down a group in the periodic table. So now we have the opposite trend. In DMF, you see the picture in the box on the right, okay, that solvent does not contain NHs or OHs, so it is an aprotic polar solvent. It doesn't hydrogen bond. Now HSe- is the least nucleophilic of the three from the same group, and then HS- is more nucleophilic than HSe-, and the most nucleophilic is hydroxide, which is in this case now the smallest of the nucleophilic atoms in the series. What's really going on here is that in a protic polar environment, you have hydrogen bonding to the nucleophile, and stronger, that is more basic nucleophiles, smaller nucleophiles like hydroxide, will hydrogen bond more effectively to a protic polar solvent than the larger, more diffuse nucleophilic atoms like sulfur or selenium. So in water, the bigger nucleophile is going to be more reactive because it's going to be interfered with less by hydrogen bonding to the solvent. In aprotic polar solvents, where you don't have to worry about that, the nucleophilic character only has to do with basicity. And so in that case, the strongest base wins, which would be hydroxide in this series. If you're comparing the same nucleophilic atom type, say they're both oxygen atoms, the more basic atom is the more nucleophilic atom. So for example, if you're looking at hydroxide, that's more basic than acetate ion. Thus, hydroxide is also more nucleophilic than acetate. Acetate's less basic because of resonance stabilizing the negative charge, which will also make it less nucleophilic. Well, now that we've seen that the solvent can affect the nucleophile, let's look more carefully at the nature of the solvent with regards to the SN2 reaction. SN2 with negatively charged nucleophiles occurs faster in aprotic polar solvents. And the reason for that is that the aprotic polar solvents will tie up the spectator cation, freeing the nucleophile to react with the electrophilic carbon, the carbon with the leaving group. So if you look at the example on the top right, there we have DMF forming a dipole ion attractive force to the sodium cation of sodium hydroxide. This pulls away the spectator ion, allowing the hydroxide the freedom to react without interference from that shielding positive charge. So it makes the hydroxide a better nucleophile. Now SN2 with negatively charged nucleophiles will react more slowly in protic polar solvents because these solvents hydrogen bond to the negative charge, getting in the way of the reactivity of the nucleophile. So again, if you look at the example in the middle, you see that the sodium cation is forming a dipole ion interaction with the oxygen of methanol, which is a protic polar solvent, and methanol is also hydrogen bonding to the hydroxide. And it's that hydrogen bonding to the hydroxide which is slowing down hydroxide's ability to react, because now it's being surrounded by these methanol molecules, which are getting in the way of it trying to react with the carbon electrophile in an SN2 reaction. So hydroxide is trying to get in there, react, and this methanol's all hanging out around it, getting in the way, diminishing its partial negative charge, slowing down the reaction. Now, I want to make sure you understand that SN2 works in all the solvents. In some solvents, such as in protic polar solvents, negatively charged nucleophiles are slower. In aprotic polar solvents, they're faster. There are no solvents, as long as it's a solvent, which is going to make the SN2 reaction not work. Okay, SN2 works in all solvents. DMF and DMSO, which you see at the bottom, are a couple of favorite SN2 solvents because they're very good at tying up the spectator cation and making the SN2 reaction go really quickly. But you can use all sorts of different solvents for SN2. Practice problem 3. Predict the major product or products of each of the following SN2 reactions. If no reaction occurs, explain. Now, we've learned about the nature of the nucleophile and the solvent as it pertains to the SN2 reaction, so that's going to be important in your interpretation of what the major product is going to be. So when you think about this, we're thinking about the fastest product that can be formed. That will be the major product of the reaction. Also, you're going to notice that there's something under the arrow now, and that's the solvent. So the solvent in a chemical reaction is typically written underneath the reaction arrow. At this point, you want to pause the video so that you can work on the practice problem. Then you can continue the video to see the answers. Answers to practice problem 3. In problem A, we have a tosylate, which is a kind of sulfonate, as a leaving group. And our nucleophile has two distinct nucleophilic atoms, a negatively charged oxygen and a negatively charged sulfur. The solvent is under the arrow, and that's N,N-dimethylformamin, or DMF. That's an aprotic polar solvent. So that means that since oxygen and sulfur are both in the same group, group 6, and we're in an aprotic polar solvent, we want to pick the more basic atom, which is oxygen, to be our nucleophile. So oxygen anion displaces tosylate and forms our product. In problem B, we have the same electrophile, and we've only changed the solvent. We now have a protic polar solvent, methanol. Our nucleophilic atom is going to, in this case, be sulfur, because the methanol is going to diminish the reactivity of the oxygen. So sulfur reacts faster, giving us our product. In problem D, nitrogen is going to react instead of oxygen in our nucleophile because nitrogen is an amine. The oxygen in the molecule shown is part of an ether, and ethers are completely unreactive as SN2 nucleophiles. So the lone pair on nitrogen will react with that primary carbon and displace chloride to form our product, which in this case is a salt. Notice that the nitrogen is gaining a fourth bond, which will give it a positive charge. The displaced chloride is the counter ion, so we actually produce an organic salt. In problem D, a secondary alkyl bromide is attempting to react with either methanol, CH3OH, or the solvent, which is an ether. Neither methanol nor an ether is acceptable as an SN2 nucleophile, so there's no reaction. If anyone happens to tell you that the methanol or other alcohols could act as nucleophiles for an SN2 reaction, they're incorrect, okay, except under extreme conditions. There is a reaction with an alcohol that can occur with a tertiary alkyl halide, but that's not SN2, and we aren't talking about that right now. In part E, you have the same secondary alkyl bromide reacting in this case with a phosphorus atom. That's a phosphine with 3 benzene rings attached to it. It's called triphenylphosphine. pH is phenyl. The lone pair on the phosphorus attacks the carbon atom and displaces bromide, giving you a salt as a product. In part F, we have a secondary alkyl bromide which is now chiral, so be wary, you have to do inversion of configuration here. Our nucleophile has two negatively charged oxygens, one which is able to resonate its negative charge into a benzene ring, and the other which is not able to do that. You want to pick the oxygen which is most basic. That's the one where the negative charge can't resonate into the benzene ring. So choosing that oxygen, we draw an arrow showing the displacement of the bromide, and with inversion of configuration, we now show the oxygen to carbon bond is in the back. One important point about drawing correct inversion of configuration. Don't change the left-right positions of the groups attached to that stereogenic center. Just attach the nucleophile where the leaving group was and invert the configuration. So notice the bromine was originally a wedge pointing towards you, but relative down. So we want to take our nucleophile, attach it, still pointing down, but in the back.